Welcome to our series on essential concepts and terminology in transportation planning. In this module, we will explore the fundamental concept of the trip generation regression model. Scientific approaches to understanding the principles of a phenomenon can be broadly categorized into deductive and inductive approaches. The deductive approach is a theory-driven approach, where an existing theory or hypothesis is established first and its validity is then verified through data. In contrast, the inductive method is a data-driven approach that derives general principles and empirical regularities through careful observation and analysis of data. Regression analysis is a typical tool used as an inductive research method. Trip generation is influenced by complex and diverse factors, making it difficult to apply a deductive approach where clear theoretical hypotheses are defined in advance. For this reason, an inductive approach that derives principles directly from observed data is considered more appropriate for trip generation analysis. Consequently, regression analysis is widely utilized. Based on surveyed data, regression analysis allows for the quantitative analysis and interpretation of the effects of various independent variables on trip generation. Moreover, because it is grounded in a rigorous statistical framework, it enables the objective and scientific derivation of empirical principles embedded within the survey data. Consequently, regression analysis is most commonly used in constructing trip production and trip attraction models. Linear regression analysis is a method used to find the best fit line that best explains observed data. The figure shown on the screen illustrates an example of simple linear regression with a single independent variable. The intercept, alpha, and the slope, beta, of this linear regression equation are estimated using the ordinary least squares method. The least squares method determines coefficient values that minimize the sum of squared vertical distances between the observed values and the regression line, which are referred to as residuals. Since residuals take positive values when observations are above the line and negative values when they are below, simply summing them would cause the errors to cancel each other out. For this reason, residuals are squared before being summed. Squaring the residuals assigns a disproportionately heavier weight to larger deviations from the line. Consequently, the ordinary least squares method inherently prioritizes the reduction of these larger errors during the estimation process. The estimated intercept represents the baseline value of the dependent variable when the independent variable equals 0. The slope indicates how much the dependent variable y changes in response to a 1-unit change in the independent variable x. In this sense, beta represents the rate of change, describing the magnitude of influence that independent variables, such as income or population, have on trip generation. Regression analysis is therefore an analytical tool that discovers relationships and associations in data that cannot be identified through mean values alone, and it enables the prediction and estimation of dependent variable values based on changes in independent variables. Once a regression equation is established, a statistical test is required to determine how well it explains the actual observed data. This requires an evaluation of the overall explanatory power of the model, commonly referred to as model goodness of fit. The most widely used statistic for this purpose is the coefficient of determination, denoted as r squared. The formula for calculating r squared is shown on the screen. As indicated by this formula, r squared represents the proportion of the total variation in the dependent variable that is explained by the regression model, relative to the variation that could not be captured by the mean value alone. For instance, an r squared value of 0.7 indicates that the independent variables in the model explain 70% of the variation in the dependent variable. It is important to note that r squared has a tendency to increase whenever a new independent variable is added, regardless of its statistical significance. Therefore, when statistically comparing regression models with different numbers of independent variables, the adjusted R-squared is used, as it accounts for the degrees of freedom associated with the number of explanatory variables. The F-statistic is a measure used to verify the statistical significance of the overall model. Specifically, it evaluates whether the values predicted by the regression model are statistically superior to predictions generated without any explanatory information. In practical trip generation analyses, independent variables are typically selected based on sound, theoretical, and logical considerations. Therefore, it is very rare to fail to reject the null hypothesis that all coefficients of the independent variables are equal to 0 in an F-test. However, when comparing two different regression models to determine which is more significant and stable, the F-statistic provides an important basis for judgment. It is essential to statistically verify whether each independent variable in the regression analysis is individually significant. The most commonly used indicators for this purpose are the t-statistic and the p-value. The t-statistic tests the null hypothesis that the regression coefficient of a specific independent variable is equal to 0. When the significance level, alpha, is set at 0.05, if the absolute value of the t-statistic is greater than approximately 1.96, a coefficient is generally considered statistically significant. If stricter criteria are required, the significance level may be set at 0.01, in which case a t-statistic threshold of 2.58 is applied. The t-statistic is calculated by dividing the estimated regression coefficient by its standard error. Accordingly, the t-statistic increases as the coefficient value becomes larger or the standard error becomes smaller. From a statistical perspective, if the true value of the coefficient is 0, the probability that the t-statistic exceeds 1.96 is only 5%. Therefore, if the t-statistic exceeds 1.96, the likelihood that this result occurred by chance is highly unlikely, and the variable is interpreted as statistically significant. The p-value expresses this statistical judgment directly in probabilistic terms. Specifically, the p-value represents the probability of obtaining a t-statistic greater than the currently observed value, assuming that the null hypothesis of a 0 coefficient is true. Consequently, a p-value less than or equal to 0.05 conveys the same information as a t-statistic exceeding 1.96. In other words, while they differ in their mode of expression, the t-statistic and the p-value provide the same statistical inference. A key factor determining the magnitude of the t-statistic is the standard error of the regression coefficient. As shown in the formula on the screen, if the observations of the independent variable are clustered closely around the mean, the standard error increases, resulting in a smaller t-statistic and leading to lower statistical significance of the coefficient. Conversely, if the observations are widely distributed away from the mean, the standard error becomes smaller, and even with a relatively small sample size, the statistical significance of the coefficient can be high. This insight has important implications for data collection in trip generation analysis. It demonstrates that in addition to increasing sample size, collecting data such that independent variables are well distributed across a broad range of values can significantly improve the ability to develop statistically meaningful and robust regression models. Regression analysis is a method that formulates the relationship between a dependent variable and independent variables using an equation to estimate changes in the dependent variable relative to changes in the independent variables. For a regression model to be statistically valid and a reliable predictive tool, several underlying assumptions must be satisfied. This slide explains the 5 core assumptions of regression analysis typically presented in statistical literature. The first assumption is the linearity of regression coefficients. Here, linearity refers to the linear in parameters structure rather than the variables themselves. In other words, even if an independent variable is transformed using a logarithmic or squared term, the assumption of linear regression is satisfied as long as the relationship with the coefficient remains linear. The second assumption is homoscedasticity of the error term. This assumption requires that the variance of the errors be constant across all values of the independent variables. When this assumption is violated, the condition is referred to as heteroscedasticity. Even under heteroscedasticity, the regression coefficients remain unbiased, meaning they converge to the true values on average. However, the standard errors are calculated inefficiently, which distorts statistical significance tests such as the t-test. This implies that relying on these metrics could lead to erroneous conclusions. To address this, weighted least squares can be used to assign weights according to the magnitude of the error. The third assumption is independence among independent variables, commonly referred to as the absence of multicollinearity. When strong correlations exist among independent variables, multicollinearity arises, leading to distorted coefficient estimates and inflated standard errors. Furthermore, it becomes difficult to reliably isolate the unique contribution of each independent variable on the dependent variable for proper interpretation. This is often resolved by removing one of the highly correlated variables or combining them into a new composite variable. The fourth assumption is independence of the error terms. This means there should be no correlation between errors. Otherwise, the problem of autocorrelation arises. Autocorrelation typically occurs in time series data and causes standard errors to be either underestimated or overestimated. To mitigate this problem, lagged variables may be introduced or generalized least squares methods may be employed. The fifth assumption is normality of the error terms. The error terms must follow a normal distribution to enable statistical inferences such as t-tests. However, if the sample size is sufficiently large, the central limit theorem ensures that slight violations of the normality assumption do not significantly compromise the reliability of the results. These 5 fundamental assumptions of regression analysis are essential conditions for improving the predictive performance and reliability of the model. Trip generation regression analysis is not usually completed in a single run. Instead, the analyst iteratively refines the model by repeatedly examining statistical indicators and logical consistency in order to identify the most appropriate trip generation model. The following 7-item checklist summarizes the key aspects that should be reviewed during regression model development. First, review the functional form of the model and its behavioral appropriateness. This involves assessing whether trip generation behavior is linear or nonlinear and, if necessary, identifying a functional form that is consistent with observed behavior. Even within a linear regression framework, nonlinear relationships can be represented through variable transformations, such as logarithmic forms. Second, evaluate the correlation and causality between the dependent and independent variables. Additionally, high correlation coefficients among independent variables should be examined to determine whether multicollinearity may be present. Third, assess policy sensitivity and data availability. Specifically, this involves evaluating whether the independent variables are predictable for future scenarios, whether the data can be collected with relative ease, and whether the variables are meaningful from a policy perspective. Fourth, verify the theoretical consistency of the signs and magnitudes of the regression coefficients. Even if statistical indicators appear favorable, a model cannot be used for forecasting if the coefficient signs are inconsistent with theory or common sense. Often, such inconsistencies arise from multicollinearity among independent variables. Fifth, review the rationality of the constant term, intercept. An excessively large intercept may indicate that the independent variables do not adequately explain the dependent variable, the trip generation phenomenon. Sixth, test the statistical significance of both the overall model and the individual independent variables. The explanatory power of the overall model is tested using the coefficient of determination and the F statistic, while the statistical reliability of individual independent variables is verified through the T statistic. Seventh, perform a comprehensive review of professional judgment and logical validity. Beyond statistical testing, the model should be checked for consistency with common sense regarding trip generation behavior. This includes verifying whether the magnitude of change in the dependent variable relative to changes in the independent variables is logically reasonable. In developing an optimal trip generation model, the choice of functional form is just as important as the selection of independent variables. Professor Kanafani categorized 4 representative demand function forms commonly used in demand analysis: linear, multiplicative, exponential, and combined functions, as shown on the screen. When constructing a trip generation model, it is necessary to consider not only the concept of finding a regression line that minimizes error, but also the consistency between functional characteristics and actual travel behavior. By utilizing derivatives and elasticity, analysts evaluate the characteristics of each function and compare them with real-world travel behavior in order to select the most appropriate functional form. For example, in the linear function shown on the screen, the derivative of trip production with respect to income is fixed as the coefficient value. This implies a functional characteristic where the increase in trip production per unit increase in income remains constant regardless of other variables. On the other hand, the elasticity of trip production with respect to income is not fixed. It varies inversely with the volume of trip production and proportionally with income and the magnitude of the coefficient. Here, elasticity indicates the percentage change in trip production from a 1% change in income, and it is widely used as an indicator for evaluating policy impacts. Nonlinear functions, such as multiplicative, exponential, and combined forms, can still be analyzed using linear regression by applying variable transformations that satisfy the assumption of linearity in parameters. As illustrated by the equations on the screen, nonlinear relationships can be converted into linear regression equations through logarithmic transformation. However, when models are linearized through transformations such as logarithms, careful attention must be paid to the interpretation of statistical measures. Since the regression of a transformed variable reflects the relationship with that specific transformed variable, statistics such as the coefficient of determination also reflect relationships among the transformed variables. Therefore, to fairly compare the predictive performance of models with different functional forms, they must be converted back to the original dependent variable, the actual variable, for evaluation. In other words, the selection of an optimal model should be based on statistical measures computed in the original variable forms. There are 2 primary types of data available when calibrating trip generation models. The first is individual household sample data obtained from travel surveys. The second is expanded data, such as trip production and attraction matrices, which are constructed by weighting these samples to represent the total population at the traffic analysis zone level. Depending on which type of data is used as input to the regression analysis, different forms of trip generation regression models can be defined. The first type is a household-based model that directly utilizes individual household data. This corresponds to the first example equation shown on the screen and will hereafter be referred to as the household model. The second type is the zonal-based total model, which uses the aggregate sum of data within a traffic zone and will be referred to as the zonal total model. The third type is a zonal-based average model that uses average values per household and will be referred to as the zonal average model. In the forecasting stage, it is not possible to predict the attributes of each individual household in the future. Consequently, independent variables are input into the model as zonal-level projections of independent variables, such as total zonal population. As shown in the equations on the screen, if all households in the household model are summed, or if the zonal average model is multiplied by the total number of households, the resulting mathematical structure becomes identical to the zonal total model. In theory, regardless of the model format used for calibration, the coefficients should have the same interpretation. For example, the increase in trip generation per unit increase in income or per additional person. Under this logic, the coefficient values should, in principle, be identical. However, when performing regression analysis on these three forms in practice, the results differ in terms of coefficient magnitude and statistical significance. This naturally raises the practical question of which set of coefficients should be selected to ensure the most stable and accurate forecasts. Starting with the next slide, this issue will be explained using example regression analyses. I will explain the input data structure for trip generation regression models using household travel survey sample data from Gangnam-gu, Seoul, Republic of Korea as an example. The table on the screen displays the coded survey responses at the household level. Here, the household is the fundamental decision-making unit for travel behavior. This dataset serves as a primary data source that preserves the attributes of individual travelers without loss of original information. In South Korea, the unique household ID is a combination of the administrative district code and a sample serial number. For each household ID, independent variables include household size, number of preschool children, income, occupation, and other socioeconomic attributes. The final column contains the dependent variable, total household trip production, Y sub h. This household-level data is disaggregate data that retains the actual variance between households. Therefore, utilizing this data allows for the estimation of regression coefficients that reflect the essential nature of individual travel behavior. It should be noted that because attribute variability is significant across individual households, regression analysis tends to yield lower R-squared values. However, this does not mean that the household-level model is inferior. To emphasize, a lower R-squared compared to aggregated models should not be interpreted as evidence that the household-level model is less appropriate. The bottom of the screen illustrates how household data is aggregated into zonal data. Suppose that a given zone Z contains n sub z sampled households. For an independent variable x sub I, summing the values across all households H within the zone yields the zonal total denoted as Tx sub z. Similarly, summing the household trip productions Y sub h for all households yields the total zonal trip production Ty sub z. Dividing these totals by the number of households, n sub z, provides the zonal average values, ax sub z and ay sub z. As illustrated by the zonal totals and averages on the screen, the data for the NZ households within this traffic analysis zone Z are aggregated, resulting in a single summary record that represents the zone. While individual variability is lost during this aggregation process, we gain a clear overview of the zonal characteristics expressed as a single representative value. Consequently, the household model is a regression equation that reflects the micro-level variations between individual households. In contrast, a zonal model does not account for differences among households and instead reflects only macro-level variations in totals or averages across traffic analysis zones. Because aggregation compresses and simplifies data variability, regression models estimated using zonal representative values tend to exhibit higher R-squared values. Therefore, even if a zonal model yields an R-squared value significantly higher than that of a household model, it cannot be concluded that the zonal model is inherently more reliable. Following the regression analysis checklist discussed earlier, let us review the results of the household-based regression analysis case study. First, the functional form of the model and its behavioral appropriateness are reviewed. In this example, all variables are specified with linear relationships. While a linear approach for population-related variables is logically reasonable, for variables such as income or vehicle ownership, it is reasonable to expect diminishing marginal increases in trip generation as values increase. Accordingly, nonlinear model specifications, such as logarithmic transformations, could be explored in future analyses, and their statistical performance could be compared. Second, the correlations and causal relationships between the dependent variable and the independent variables are reviewed. All independent variables are considered to exhibit strong correlations with the dependent variable, trip production, and to be behaviorally and logically plausible. Third, policy sensitivity and data availability are reviewed. While future forecasting for population-related independent variables seems feasible, accurately predicting future income is likely to be difficult. If future estimates are hard to obtain, the model becomes difficult to apply in practice, even if the statistics are favorable. In such cases, one might consider using a proxy variable that is highly correlated with income but easier to forecast for the future. Fourth, the theoretical consistency of the signs and magnitudes of the regression coefficients is evaluated. The positive signs, reflecting that trip volume increases with the number of household members and workers, are consistent with common sense and observed travel behavior. Furthermore, the negative coefficient for the number of preschoolers is also consistent with real-world behavior, as households with preschoolers often face constraints on outdoor activities. The magnitude of each coefficient is also judged to be within a reasonable range considering the daily activity levels of travelers. Fifth, the rationality of the constant term, intercept, is reviewed. The intercept is approximately -0.6, which is not considered excessive as a proportion of the error not captured by the independent variables relative to the total trip generation scale. Since the intercept is not excessively large, it can be inferred that the portion of trip generation explained by the independent variables is relatively significant. Sixth, the statistical significance of the overall model and individual variables is tested. The F statistic is very large, indicating high significance for the model's goodness of fit. Although the coefficient of determination, r squared, is 0.333 and may appear low, it is considered a favorable result given the substantial variability inherent in disaggregate household-level data. Since the t statistics for all independent variables significantly exceed 1.96, they are analyzed to have a significant impact on trip generation at a confidence level of 95% or higher. Seventh, expert judgment and overall logical validation. This household model is judged to possess both statistical stability and behavioral logic. Let us compare the analysis results of the three models using the Gangnam-gu case study. As shown on the screen, the R-squared value for the zonal total model is overwhelmingly high at 0.89, followed by the zonal average model at 0.52. In contrast, the household model is the lowest at 0.33. However, model performance should not be judged solely on the basis of R-squared. It is essential to recognize that each model is calibrated using different types of input data. The high explanatory power of the zone-based total model does not stem from a superior representation of travel behavior, but rather from data characteristics that implicitly embed zone size. As a traffic zone increases in size, the totals of independent variables like population and income increase accordingly, and trip generation correspondingly increases in proportion. This means the explanatory power stems more from the scale effect of the zonal size, rather than the behavioral impact of income or population on trip generation. Furthermore, since individual errors in trip generation accumulate as the number of travelers increases, the cumulative error, and thus the error variance, grows with the size of the zone. Consequently, the zonal total model suffers from heteroskedasticity, which in turn reduces the stability and reliability of the estimated regression coefficients. In contrast, the zonal average model does not exhibit a scale effect. However, during the averaging process, household-specific variability is eliminated, and the variance of the data decreases in accordance with the central limit theorem. These differences in input data characteristics are why the zonal average model yields a higher R-squared value than the household model. Moreover, because the variance of the error term still differs by zone size, the zonal average model also likewise faces issues with heteroskedasticity. In the household model, all variables were found to be statistically highly significant. In contrast, in the zonal total model, vehicle ownership was statistically insignificant, and the coefficient for the number of workers resulted in an illogical negative value. Similarly, in the zonal average model, the coefficient for the number of workers was estimated as a negative value, which is illogical, and the coefficients for both vehicle ownership and the number of workers were estimated to be statistically insignificant. The reason why the R-squared value for the zonal total model is nearly 0.9, while the household model only reaches around 0.33, can be visualized through the scatter plots on the screen. The scatter plot on the left, which corresponds to the household model, shows that the observed data points are widely dispersed. This pattern reflects the inherent heterogeneity of travel behavior across individual households. Because the residuals are large in disaggregate data, the R-squared values tend to be lower. However, these data points reflect actual travel behavior exactly as it occurs. In contrast, the zonal total scatter plot in the center shows condensed aggregate data points scattered along a straight line. This is the scale effect phenomenon. As the size of a traffic analysis zone increases, its population increases, and consequently, the total trip generation volume grows proportionally. This proportional relationship creates an artificial linear correlation in the data, leading to inflated R-squared values. In this case, the high explanatory power reflects not a causal explanation of travel behavior, but rather a statistical distortion arising from independent variables increasing proportionally with zone size. The zonal average scatter plot exhibits a tightly clustered distribution because the differences between households are condensed into means during the averaging process. In accordance with the central limit theorem, data variability is reduced, resulting in a more concentrated pattern. This dense distribution of data minimizes regression errors, which is why it tends to produce higher R-squared values compared to the household model. To ensure a fair comparison among the three models, we evaluated their coefficients of determination, or R-squared, under the same reference state as the zonal total model. As shown in the equations on the screen, we applied the same zonal total input data, that is, the common basis, to all three models to estimate their predictions using the coefficients derived during the calibration stage for each respective aggregation level. Using these predicted values, along with the observed values and their mean, we computed the total sum of squares, SST, the regression sum of squares, SSR, and the sum of squared errors, SSE. Based on these values, we recalculated the R-squared value for the household-based model and the zonal average model. Note that for the zonal total model, we simply used the statistics from its initial calibration as it was already calibrated using zonal total data. Since all these R-squared values were calculated on a unified predictive scale, we can now directly compare the predictive performance of the three models on an equivalent basis. The recalculated R-squared value for the household model is 0.867, and for the zonal average model, it is 0.881. These figures show no significant difference from the 0.983 of the zonal total model. Given that the zonal total model was optimized mathematically for the zonal total dataset, the explanatory power of the household model is effectively comparable. In conclusion, the household model is the most appropriate predictive model. It avoids theoretical issues such as the scale effect and heteroskedasticity, while intrinsically reflecting the behavioral causality of individual households. Furthermore, as this case study demonstrates, its predictive power is highly competitive under common conditions. Therefore, the most scientific and rational approach is to estimate regression coefficients using household-level data to capture behavioral causality, and then apply those coefficients to predictable zonal-level input data to forecast future trip generation. In the next module of our series on essential concepts and terminology in transportation planning, we will focus on the topic of trip distribution. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.